There we go. Okay. Now I think everyone can hear me all right. Let me pull up the chat real quick. Should still have it. All right, can we all hear me okay? All right, can we all hear? There we go. All right. Might hear a brief echo. That was my phone just making sure that everything was good. All right. Well, we're going to wait a few more minutes because we're still a little early. But just want to make sure that this time we didn't run into any major issues. I'm going to keep the chat up here in the top corner because my usual co-partner, John, he's out today. I'll also have the, I'll occasionally check the forums too, just to make sure that we don't have any questions over there. There's a slight schedule change for those that haven't seen it yet. So I moved down, let's go look at the schedule here on the forum. The slight schedule change involves when we're going to be doing pose detection first. That's going to wait until after 2 weeks from now when we do key point and object detection because it's a hybrid of the two. And today we're also going to go over the internal API and sort of look at what all that does, what is the PIL image and everything like that. So I'll explain that again in a few minutes. But in the meantime, if you have any questions from last week, feel free to use this time to ask me anything. So along with after item, we have a bunch of other after and before. I see when are they applied and have some examples. So we're going to go through that a bit today with the internal API walkthrough, along with, I believe we're going to go into it in the cross-validation notebook as well. So when we get to there, I'll kind of explain what the whole before and after does. But to a certain extent, think of the before, like if we do a before batch, that's the same as before we call everything into our batch, we want to apply some sort of transformation. Whereas after batch is after we've collated everything and we grab our batch, we want to apply X, Y, Z to it. But again, we'll kind of dive more into detail when we go over the internal API from scratch and kind of what all's really going down in there. Also, if the lights randomly go off, I'll fix it in a moment. That's just the room I'm in. It has a timer, and today it's deciding to turn off every like 5 minutes or something like that. So bear with me while I deal with that. Haha, that's the secret. Few more minutes. What's up?
I'm working on some projects tonight.
Okay.
I'm gonna hit up the stream.
So when trying to make a data loader from a data set, do we always have to do .dataloaders? If you mean from a data block, yes. Actually, let me make sure. Yeah, okay. Yeah, if we're trying to go from the DataBlock API, yes. If we're trying to go from the low level, the lowest level, no. Take a look at the MNIST notebook, and it kind of goes through how we go about this on the super low level. We're going to kind of go through that a little bit today. But if we go back to MNIST, we have our data sets that we made. And then from the data sets, we create the data loaders. Does that answer your question? Essentially, yes. So you create the data set first, and then you make the data loaders. Bear with me one moment while we set up here locally real quick, and then when everything is good to go, we will go ahead and roll with it. All right, we are all good here. Glad that answered your question. Let's go check what Mr. Fabulous. I like to their name differently inside the notebooks themselves. Yeah, so if you open the notebooks, sometimes they might be named differently in Colab. That's because Colab operates off of its own special notebook structure to get its names. So those were when it first started. Go by what they are in GitHub. Eventually, I'll get around to fixing the names of the notebooks themselves. So that way, when you open it from Colab, it looks like how it should look. But otherwise, we're going to try and go with this setup today. As I mentioned earlier, my partner, John, he is out for the day. He has some homework to do. So we're going to try and keep the chat over here and roll with this sort of setup. So first, let's go through a little bit of announcements. So there's some major changes to the API that came out this week. I've updated all the notebooks, but the biggest bits are .DataBlock is now data loaders. The data block now includes transforms, so your item transforms and your batch transforms will be passed in there along with it. And then if you were trying to get any data loaders from your data loader object or your data bunch object, it's instead of train DL or valid DL, it's now train and valid. And you can also index into those two. Along with that, there's a few updates to the schedule. So I pushed back when we're going to go through and do the pose detection, specifically because that involves components from both bounding boxes and key points. So we're going to save that until after that lecture. Along with that, today we're going to go over the internal API a bit and see kind of what's going on below the surface, what's PIL image, and kind of how do you go about, in a brief way, understanding how to build custom implementations. We'll go really into that when we get to the heat maps and the pose detection, but this will just be a brief intro. Along with that, as we have now a lot of notebooks, everything we're going to be working out of is in the computer vision folder in the repository. Besides that, Jeremy just announced the newest course, so congratulations to those of you that got invited. I believe it starts in a few weeks, so it's going to be perfectly right when we finish computer vision. So for those of you watching, you'll have a decent understanding to what's going on whenever you walk in. So today we're going to go over multi-label classification, kind of what that deals with, along with how do you tell your model, I don't really understand what I'm looking at, a question that I've seen a lot on the forums. We'll also go a bit into what's called k-fold cross-validation. It's used a lot with tabular. There's a lot of tabular examples for this, but how does it look like with the API for images or really anything, as we'll see? And then we'll sort of walk through the internal bits of the API and figure out what all's going on there. So first, let's install the libraries. And we're going to grab everything from Vision today, as this is a multi-label classification based on satellite imagery. So we're going to use the planets dataset, and it has multi-label in the sense of we're trying to describe the scene, and it's not just forest or tree, it's, forest with a river, forest with water. We'll go through, along with this, a few different ways of how the DataBlock API works, how you can go about customizing it a little bit, and how flexible it is. So first we'll go ahead and just grab our data. So it's just going to be our usual untar data, and we specifically want the labels. So this will be from our labels.csv that we see right here. And if we look at how it's stored, we have an image name followed by some tags that are separated by spaces. So we have partly cloudy primary, clear, cultivation, primary weather, and what have you. So let's go through the first method in the data block. Now remember, one of the changes I said is we need the batch transforms. When DataBlock summary, when I work with it a bit more, because it was just added, I haven't had time yet. Probably next lesson we'll go through kind of what that looks like, but it's a neat, nifty way to debug your data blocks, and that's why we have to include the transforms here. So we'll just use augmentation transforms here, and not really worry necessarily about anything else. And so for our data block, we want it to be structured where we have an image block. Bear with me. There we go. That might happen occasionally. The timer's a lot shorter this time around. So we'll have our input as an image block, our output to be multi-category. Now our getX, we're going to use column reader, where we're going to grab the first column here, and we're going to include a path to where our training images is, because all it's going to get from column reader is just train 12664. So we're going to provide it the initial path along with what the ending file name should be for our X. So this would be grabbing our images. We're going to split by a random 80-20 again. And for our Y, we're again going to use a column reader, where we're going to grab our tags that are separated by a space. And then finally, we're going to pass in our batch transforms. You'll notice that we don't have any item transforms for our resize. This is because everything is already the same size from this data set. Now, from here, we're going to do a .dataloaders. We're going to create our data loaders by passing in the data frame, our source. And we can make sure everything works by doing a show batch. We can see that our delimiter for the show is this semicolon, and everything looks to be all right. So now that we've seen one way of going about doing this, let's try a more Pythonic way with lambdas. So we're going to do that so we get rid of this column reader. If you're more familiar with lambdas or you feel better using lambdas, this might be one way of going about it. So let's restructure our getX. So getX is expecting some sort of path to be returned. Now we can work with this by using what the planet source was, the train, and then using Python's f string in order to then grab whatever our x is and grab their file name. Now, what in the world is this x0 that we see here, though? That doesn't really tell me much. Let's take a look. If we get the values from our data frame at one particular row, we can see that this 0 is our file name. So anytime that we're passing lambda x, it's always whatever the values are for our input that we passed in, so that data frame. So here, if we call getX, we will grab a path to that training image that we wanted. That's very nice. So, and it's a clean way to grab our paths compared to what we had before. It's a little bit nicer to read. And so now let's do our getY, which is going to grab the second item that pops back up, and we will split the string that returns by spaces. And that's it. So now let's throw that back into the pipeline. So our getX is just getX, our getY is just getY. Everything is still structured the exact same in terms of data loaders, so we just pass in the data frame, and we can show a batch. Yep.
I'll come late because I just.
All right, sorry about that, everyone. So now we're going to use a getItems function. Now, what getItems essentially does is instead of separately grabbing x's and y's, we just do it all at once. And it just expects a tuple of x followed by y. So here we're just going to say planet items. That's going to return our path to the image, and then splitting up the target again with their strings. Now, if you notice, we have image name and targs here. That is because we have our image block, so it expects some sort of image name, and then targs because that's just our y. So now the data block kind of looks like what we have going on here, where instead of a getX, getY, we just have getItems, and it's the planet items function that we called right before. Again, we can just call our data frame here, show a batch, and we can double check that everything is really working how it should be. So that's the sort of 3 different ways that you can go about customizing the DataBlock API in order to work with whatever you might need, make it as clean or complex as you might need. And now that we've sort of gone over all that, let's go ahead and train a model. So we're going to use pre-trained ResNet34, and since this is multi-label classification, we want to use a different accuracy function than just accuracy, because accuracy assumes that we have just one particular value that we're outputting, whereas we have 1 to n, where n could be any total number. So we're going to create a CNN learner, pass in our data loaders, the architecture, along with our metric to be accuracy of multi, and our multi-label accuracy. There we go. And now what we want to do is, so when we pass in this multi-category data bunch, CNN Learner is going to see that we're doing multi-label. And how is this pipeline similar to pipe from earlier? Sorry. How is this pipeline similar to the pipe from earlier? Does the pipe exist by itself still? So the pipeline is sort of a precursor to the data block in a way. it's one step lower. We're not necessarily going to go through it as much, but it's kind of the same way in the sense of this is still a pipeline where we're getting our x's, what they want to be, what our types are, how we want to split them, and then what transforms do we want applied. So this exists by itself, and then we have to do .dataloaders and pass in our items in order to do anything with them. Does that answer your question? So back to the, well, first we'll wait. All right, so from here, let's go back to that loss function. So the difference between multi-label and non-multi-label, or singular classification, is we can have any number of, but no specific pipe. So pipe does exist. If you look in, I can try and show an example of where pipe could be used. Think of pipe as once you get your input, we can send it through a pipeline of transforms in order to get it to something else, but that's not necessarily getting the input. It's just once you have the input, send it through a pipeline of transforms in order to get it ready. Maybe that'll answer your question a little better. So now what we have instead for our default loss function is this BCE with loss logits. Basically, instead of just condensing it to one, we perform a sigmoid activation. And then from there, we see if any of our x's are above a particular threshold. If they do, then we're going to assume then that they are one of the labels. And we'll see a nifty little hack for this a little later. So now we can declare the loss function manually if we want, but if you check the loss function, it should automatically be it. Go ahead and find our learning rate. You can convert our model to mixed precision to make it train a little faster. And we'll go ahead and train. You guys can run that real quick. I'm going to go around and make sure that we're okay over on my end. Let me know any questions you have getting up to this point. All right, so from here, we can unfreeze and find another learning rate and fit again, just like we normally do with transfer learning applications. So after you've run it for a few more epochs, we can see that our accuracy multi is very, very high. And what that really means is the only results that are outputted from the model are just our 2 to 3 different labels that we have. And so if we do show results and see how the model did, we can see that brightly color-coded for us, we can see where the model did good and where the model did bad and what the predictions versus the actual truly were. And that's really all there is to multi-label classification. It's just make sure your X's and your Y's come in and make sure your Y's are some form of a list. We'll see about that in a moment. And then the default loss function is this BC with loss logits. And this is taken directly from the fastai library. So there's nothing special done here. Now let's migrate over to some cool things, because starting this lesson and beyond, now that we've kind of gone into the intro, we're going to take a look at some weird applications and what we can really do with this library. So the first bit is we're going to go back to pets. And I want my model to tell me if it doesn't know what something is, if it's neither a cat nor a dog, for instance. So we'll go ahead and grab the pets folder, the pets data set again. And the difference between utilizing multi-label versus single label is multi-label expects your items to come in as a list. And so what that means is if we want, say, single label classification to turn into multi-label, wrap it as a list. And now what we can do is pass this into our get Y. So we still have the regex labeler and everything is set up exactly like the first lesson. But now we also pass in this multi-label transform. And what it will do is anytime that we grab our Ys, we'll first run the regex labeler, and then we'll convert it into multi-label classification. And now we are doing exactly that. As you can see, the show batch still shows just one label. And so that's all that our model is going to be trained for. And so let's go ahead and train with that. Now, with our accuracy multi that we have here, I can define a threshold of when I want it to assume that it got it right. And so we're going to say anything that's above 90%, we're assuming that it knows what it is. So we'll fit for epochs. You can see we immediately got 99%. Let's see how the results look. Now you can see that it's color-coded like before. This is another hint that we're actually doing multi-label classification instead of just a single. And let's try some random image. Go ahead and search for any random image you want. And you can upload it to Colab and do this PIL image create in order to create an image. We'll go through what that actually is in a moment. But if we pass that image into our model, we can see that it doesn't know what a donkey is, which I'd expect it not to, considering it's just trained on cats and dogs. And so this is one way for you to go about making sure if your model doesn't know what it is, make sure that it can tell you, compared to using accuracy, where it always will tell you at least some prediction. There's a few other ways that you can go about doing this, like Bayesian neural networks are another example. I won't be going into that. We will just cover this in terms of the I don't know. But there's certainly a lot of discussion on the forums that go about other techniques that people have found. All right, so now let's move on to another funky bit. Looks like we have another question coming in, but in the meantime, so the next bit we're going to go over is what's called k-fold cross-validation. And it's a, yeah, if you briefly couldn't hear me, I'm just talking to the guys here that are trying to get set up. So don't stress out over that. So what exactly is k-fold cross-validation? It's a popular technique used especially in the Kaggle competitions for getting the most out of their data possible, and then through what's called ensembling, we can actually get better predictions because we're using 5 to 10 to 15 to as many models as you possibly want on this one source of data. And it really allows you to get the most out of your data, but the cost is it requires more training, more computational power when you're running it, and depending on how big the data set, it can be more costly. So what we need is a training set and a test set. We don't need any sort of validation per se, because we need some way to standardly grade how all the models are performing. This is where that test set comes in. But for us, it's going to be labeled because we need some way to quickly get its accuracy. And we only have a training set. Threshold of 0.1 is 90%. Yeah, I think you're right about that. I think I was incorrect on the threshold. So if we have 0.9, then it will result in whether or not it's has a percentage of 90 or higher. Thank you. The way how cross-validation works is we're going to separate our data into two different bits. We have the 10% that's training, and the 10% that is our test data, and 90% that is our training. And from there, we're going to take that 90% worth of data and generate n data sets off of it. The difference being we're slowly shifting what our validation is. So no two models see the exact same validation data, but they all are graded on the same test data. So for us, we're going to use a data set called ImageWolf for today. We're going to go into more about what this data set truly, why it's important. It's one of the ways that you can test new models out that you're trying to see if they're state-of-the-art in a fun little competition. We'll explore that more when we do state-of-the-art models next week. But you can see that we have a validation folder and a training folder. We're going to go ahead and grab some batch transforms that normalize everything, along with some item transforms that do some resize. And today we're going to use index splitter. And the reason why is k-fold expects a bunch of indexes to declare what our validation set is and how we can sort of move it along a line. So the first thing I'm going to do here is randomly shuffle the training images. The reason for that is if by happenstance one class that's not in our training set happens to be in the validation set, then we're going to throw a mismatch error because it's going to say, well, I was expecting 10 classes to pop out, but you only gave me 9. This way we guarantee that everything should all show up there. Now the next thing we need is a starting value and an ending value for when we want to define our validation set. So we're going to take the first 80%. That's what this does right here. And then we're going to grab from there the indices from the starting value to the ending of our training images. And so we're going to pass those into an index splitter that will go through and say, at these particular indexes, I know to split everything after index 9,000 into the validation set and everything before it into the training set. Instead of randomly splitting now, we're sort of going through this list. And that's how index splitter works. It expects a list of all of our items, and then we'll split it accordingly. So now, one thing that's nice with fastai2 is we can have unlimited data sets tied on to any one data loader. So it's not just train and validation. In fastai1, this was train, validation, and test. And test always had to be unlabeled. So here, what we're going to do is first turn our splits into a list, and then add to that every indice after our training images, because that is what we expect our test images to be. So now we have a split list where we have our training data set, which is the first 7,220 items, 1,800 as our validation set, and another almost 4,000 images that we're expecting as this labeled test set. So from here, we can create our data sets. And the simple way of passing in our combined list of file names is just add them together. And it will go through and run the splits that we defined right there. Now we can double check this by first making sure that we can open one item from our training set. And then we can see that this subsection was applied if we call number of subsets. So now we have 3, which is our training, validation, and this constant test set that we're always going to have. We can then data load it, show the batch, and make sure everything looks okay. Now, if we do just a quick baseline, we're going to not use a pre-trained model here. And we're going to get about 8%. It's a hard data set, especially when you're training from scratch, so don't expect magical performance off of here. And now let's see how we check it. We can do this by calling learn validate, and all we do is pass the index of what the data set is. So in our case, we had a third data set, so this is index 2. You can see that we got about 1% accuracy after one epoch. That's about expected. So that was a lot that I just threw at you guys. Any questions yet? All right. So now let's actually go into k-fold cross-validation. We have all the setups that we need. We know how to split by a list of indexes, how to create this labeled test set, and now let's put it all together. So we're going to use the scikit-learn model selection library to grab our k-fold. And the reason why we need this compared to stratified k-fold is this will just split our indexes for us. So we're going to create a k-fold object and say we want to do 10 different splits or 10 different models. And we can make sure and see kind of what's going into each for our training and validation if we look at what the split is. And so the last bit that we need to do now that we have this k-fold object, is actually build our training loop. It'll look a little bit different and a little bit more complex, but let's sort of walk through what's going on here. So you can see that the second option here grabs our validation indexes. So we're not going to care about what the training is because we only care about the validation. So we'll go ahead and create an index splitter with those validation indices. We'll then split our training images again, convert it to a list, add onto it our test images, create that data set again, create our data loaders, call CNN learner, train, and then from here, I want to keep track of two things. I want to keep track of what my validation percentage was, along with the raw predictions that we get on our test set. And you'll understand why we're going to be doing that in a moment. Compared to, say, validate. If you just had some sort of data set where you wanted to do it very quickly, you could pass in the index into validate, but here we're not going to do that. So we're going to go ahead and grab the percentage and add that to our validation percent list. And then we're going to get the predictions of our test set and pass them into A. B contains the answers, but we don't care about those. We just care about A. And so this will take quite a number of minutes to run. On your guys' end, I believe I clocked it in at like 20 minutes, even though each epoch is only a minute and a half. This is due to the validation and the getting the predictions. So it will certainly very quickly increase in complexity and time. But now let's go through and ensemble it. What does that look like? So ensembling involves averaging the raw predictions from our model, and then from there taking what should ideally be a solid mixture that has the best results. So let's first just make sure that that B truly has what accuracy we're wanting. We can double check this by grabbing the first list of our predictions and pass it through the accuracy function. And if we go back to what the first model actually was, we can see that was about a 23%. So if I got something radically different like 18 or 5, I'd worry there. But here we just got about 26. So we did a little better, which is about what I'd expect. We can go through and make sure that this looks the same for all of the predictions, and they're all within that 23 to 25% threshold. So the goal here now is assuming that more models will get me a better result and they can generalize a little better. We should probably want to beat about 26%. Why the raw and not the average of the class from each prediction? So the reason for that is we want the raw percentages for each particular class on every prediction. So if you do get preds, what it winds up giving you is, say we have item A, it's 16% dog, 20% cat, 30% say Chihuahua, and all of that will sum up to 1. We want to take all of those rounded predictions and average all of those together. That's how ensembling works. And you'll notice very quickly what that can actually do. So now we're going to go ahead and add all of them together. And if we look, this is what I meant by those raw predictions when we sum them together. So each of this is just one of the 10 classes. One moment. There we go. Well, I actually waited a lot longer than I thought it would this time around. So you can notice that it's no longer on a scale from 0 to 1. This is because we just summed them all together. And so now if we divide this by the total number of predictions that we had, our accuracy is almost at 29%. From the absolute worst case, that's an increase of almost 6%. From the best case, that's an increase of 3%, which is one reason why when it comes to Kaggle competitions, this is extremely valuable. From a production standpoint, you're running multiple models at once, which might not necessarily be the best idea unless you have those computational resources. But certainly with Kaggle, it can make a difference. Any other questions on kind of this technique as a whole that I can go through again? So how we went from 8% to 25% on a subset of data on one epoch. So, that is actually a very good point there that you have. I didn't notice that before. I honestly don't have an answer to you on that one. That's a very good observation. I'd be curious as to what's happening on the internals there to get it to that way. So you ran 23% on that line? Yeah, probably was cool. So Clive here got about 23% when he ran the quick baseline. That might have just been an offset of something. The default learning rate might have been too high. Your accuracy can certainly be different than this initial one. So. All right, so now that we have that going on, and if you guys are running this code, this will take 20 minutes to run or so. So don't be surprised if this is going to take a long time. All right, so we're going to move on to a request. And this was to kind of go about the internals of the API a bit. So like, what is PIL image? And what are these blocks that we're doing? First, make sure I don't have to install everything again. I don't. So we're going to go through a very basic example of how we take an image and convert it over into how the pipeline expects, along with an example Y, which for our case will be points, mostly because it's a simple one that you have to worry about both creating the object and how do you deal with the transforms. So for the first example, we're just going to use an image of a cat. So we can use download URL and just get our cat. Now we're not going to go ahead and do PIL create yet. We're going to take a chapter off of the part 2 from this year, and we're going to try and build it and understand what's really going on there. So let's kind of look at what PIL image does. If we call PIL image with our double question marks, we can see where it's coming from, this vision core. And this is all that code looks like. It's just PIL image with a PIL base when it comes from the inheritance. Okay, that doesn't tell me anything. So let's go dive down one chapter below into PIL base. And this is where we're starting to see exactly what this sort of type expression or what these objects should really look like. So there's a lot going on there. From a base standpoint, everything is going to have a create and a show function. But let's try and break this down all the way. So we have this image type, and what that really means is it's from the pillow library. You can see that it's just an image object from pillow. So we're saying that we're going to expect some sort of pillow attribute, And as I said before, we want a create function and we want a show function. And so we can see this if we call PIL image create and image.show, we have our cat. So what do we learn right there? We need a create and a show function for pretty much anything that we want to do. The show function is used for when we have like show batch. So while it's not necessarily required, make sure you know what you're doing if you want to run without it. So now let's look at kind of what the image block is that we saw in the previous lessons and even just a little bit ago. So it's a function that has a class type of PIL image that we just saw before, grabs some sort of image and loads it into the pillow library. And we want to return this transform block that calls class.create and applies some sort of these batch transforms into float tensor. All right, now it's looking a bit more familiar. We're calling PIL image.create anytime we want to grab the item, and the assumed batch transforms is this integer to float tensor. And that's all it is, really. The transforms that can later occur, we'll look a little bit into that with the points, but that's a very basic example of what an image would look like. We assume that whenever we want to get our types and want to open it up, it's going to be a PIL image that's going to run PIL create, and the batch transforms will convert it from an int to float tensor. Now let's convert this over into something that's not necessarily an image. So we're going to look at points. So that's your x's and your y's. So if we take a look at point block, we see that we have this transform block again that calls TensorPoint.create, and now we have some item transforms called PointScaler. Let's sort of dive down into what really is going on under the hood. So the goal of TensorPoint is to get an input of a list of these x's and y's and convert it to a tensor. That's it. Nothing about transforms, no sort of raw input for our model. Just take some x's and y's and convert it into a tensor. So we're going to go ahead and create a class. Now we're going to inherit from TensorBase. And basically what you need to know about TensorBase is just assume that everything that you want to return will be a tensor of some degree, or it should be. So we're going to create a create function that takes in t. And what t is going to be is some list of points. We're going to create a tensor off of it and have it set to be a 1x2 list, and make sure that they're floats. This is so that way whenever we go about transforming the image, they can still be in the right positions. Now, with what I just said there, though, we might want to keep track of what that image size is and make sure that we know kind of what we're starting with. So let's go ahead and make that an input. We'll go ahead and say image size. By default, we have none if it's just calling on its own, and pass that into our TensorBase call right here. So let's go ahead and try it. We can grab the image shape and see that we have a 1900 by 2300 pixel image. We'll go ahead and make some random points, 1000 by 100 and 200 by 300, and create some tensor points off of that. If we take a look, no transforms have been applied to it yet or anything. And so we just have this tensor that has our 1100 and our other key point. So now we need that show method I described earlier. And for our case, since we are working with points, we'll go ahead and use a scatter plot. Now the assumption that we're going to make here is anytime you're going to show these, you're going to pass it on top of an image that is going to overlay it. So we'll go ahead and first make sure that fig size isn't in our show. If it is, then we want to use it and not the default keywords. Then we're going to want to take our tensors and bring them back into a view. And when we say self here, the reason for that is self is whatever our input is. Whatever one line of our item would be after we do this create function. And so from there, we'll go ahead and make a scatter plot on our axes and return it. That's all we're doing. So let's go ahead and see what happens. Uh-oh, we have an error. What went wrong? Remember, I said it needs an image to overlay on top of. So let's go ahead and call show again and pass these axes instead into it, into that show call. And now we can see our points pop up here and they pop up here. Now there's a few other bits that we need to do. What we're going to go and do here is say, whenever I'm dealing with key points in general, I want my loss function to be mean squared error loss flat. And right now, it doesn't know that. So CNN Learner wouldn't know that whenever it's trying to grab the loss function. Let's go ahead and do that. We're going to make this little my TensorPoint create object, and we'll say that it's a transform based off of the create function that we just made. We'll go ahead and give it the property of a loss function and declare that as our mean squared error. And now we'll go ahead and replace the original .create function with this new one that has the attribute of the mean squared error loss flat. So it looks like we came pretty close. How do we do compared to the source code? Only thing we didn't have were these show arguments, and that's just whenever we call show, we can pass in, or it assumes that the color is red, and among other things like that. Otherwise, it's all exactly the same. And this is exactly from the fastai source code. So we can create this sort of 1x2 tensor that will overlay onto an image, and I can work with it. All right, that's great, but what if I start applying transforms? What if I start resizing my image or warping it? How do I make sure that they get affected and scaled accordingly? Because right now they won't. They will just output and assume they never change. Let's go ahead and create something called a PointScaler. Remember, this is the second part of that item transform. And what item transforms do again is anytime we call the particular item, so we call a resize, it's done first before we chuck it into the batch. So what do these transforms exactly look like? They all follow a pretty basic structure. So we have an order, and this order tells us when do we want it to occur. If we have an order of 1, then it goes first. If we have an order of 99, then it's at the very, very end, just before we finish pulling that batch. We have setups, and setups are kind of an initial way to prepare our data. For instance, we can figure out a data.c from here. Encodes, what are we doing when we're passing our image through the pipeline and sending it through and transforming? And decodes is sort of how do we travel backwards to a point where it's presentable as a .show method. So we'll walk through sort of the start of PointScaler. We want it to have an order of 1 because this is going to be happening right as we do our item transforms and right as we resize. we're going to go ahead and keep track of, do we want to scale our y's? And will they come first? And then that's it. That's for our initialization, all we want to do. Now from here, we'll do our setups. So we want to understand the total available points in that part of the data set. We can use an attribute called .numal to see just how many there are. So if we take our tensor points from earlier and do a .numal, we can see that we have 4. And so for setups, what we actually do is we pass in the data loader, and we say that the item is the first one out of the data loader at index 0. And then we see for every single item in there, if we have a tensor point, then we will say its .c is whatever this numal is, or .classes. Now from here, how do we go into this sort of encodes, decodes, and how does that all work? So encodes and decodes operate under the assumption of, if I have, during the transformation process, if I have a particular type available to me, then I'll run the transformation on it. So first we're going to build a little helper function just to see what our current points are. So we'll do this grab size here, which will just take the shape of our x and make sure it's a tensor. And if not, then we'll just call the size. And now let's get into the encodes and decodes. And what we want to do here is, if we have an image, go ahead and grab our y's. Go ahead and grab what our points are. So we'll have this encodes that takes in an x that can either be a PIL base. Remember, PIL image inherits from PIL base. If we go all the way back up quite a bit, remember, PIL image inherited from PIL base, so it assumes that it's something from the pillow library. And then, or it can be what's called a tensor image base. I haven't explored quite what that does yet, but assuming it's a tensor image of some degree. And then we will return the sizes from our y's. That's all we're doing. First, just get our points at some point during the transformation. And now let's make another one that scales the points. So we're going to make a quick helper function here to sort of scale our points along with the new sizes that we're going with. So to test this out, let's say we have our points, scale them to some image that's 224 by 224. This is what our resulting points would wind up looking like. And let's sort of look at what this would do in an image of our degree. So the points that you have here are the 4 corners. And I did this so we can sort of see an example of what winds up happening. So we're going to pass in our TensorPoint create like we did before. One moment. In order to build our TensorPoint tuple, we have multiple points here, and so that's why this is happening. And let's go ahead and show and double check that they are in fact the 4 corners. And now we can scale those points, and this is what our output is. Now, to understand kind of why I wanted us to go about doing this, the order is the exact same. You can see that 0, 0, when we transform it, gets converted into the -1, -1. And so anytime that we're trying to deal with maybe something that's not there, we want it to be this -1, -1, or 0, 0. And then we have, 16 and 20. All right, well, I'm sure your next question is, well, if it's just, 16 and 20 for a 224 by 224, then I don't have to worry about anything else. That's it. It's done. Let's try it out on a different image just to be sure. So this is a different image. We're just going to pass through what we did before, pass in 4 points that are the edges. And you can see that we have a bit more of a rectangular image here. So let's go through and scale those points again to this new image. You can see that it doesn't quite add up. They're not quite the same anymore. But 0, 0 is always this -1, -1. So do with this information how you will. We're going to kind of take a look at this a bit more in the key points lesson, along with in the image regression. So now we have them scaled, we need to undo it. And basically, we're just going to perform the inverse of the formula that we had above, pass in our image size, and that's it. So we have our scaled points. Want to make sure that we get the same ones back. And we do. That's exactly what our input was from the first time. And so from here, we can have it cropped, rotated, what have you, and it will always pretty much keep track of what's going on. Let's compare that to the original base code. You can see that we were really just working directly with what's going on in there. When we were doing our last encodes, which I didn't necessarily show you guys, apologies for that. Remember how I said we want to keep track of what it's expecting? So by the time we're done with here, we want it to run far enough to where we convert everything into these tensor points. So we can generate an encodes and decodes that assumes we're at an instance where we have tensor points, which ideally should be happening after we've cropped and scaled our image. And now we can call our scale points and our unscale points and grab it and pass in everything we need. So our size, if we want to scale or not in terms of our scale points, and in terms of unscale, just the raw values and what the size of our image is at this particular moment. Now what we just created was the very low level API where we can pass in our say our item transforms, and we can say, PointScaler with, we can say do scale equals true, and we can have our type transforms be the tensor points that we had. And so now, how do we make a block with our new bits? This is going to look very similar to what we had before, where we say on our types, I want to do the TensorPoint create, and on the items, I want to do the PointScaler. And so now if we want to generate any sort of custom transform that would be applied, we can use the patch decorator. And so what the patch decorator can do is, say we have our tensor points and we want to flip them left, right. It will run a specific version of flip left, right for tensor points. So if we look at fliplr's source code, which we can find if, I'm going to bring up the Git repository real quick. The transforms all live in whatever subsection you have, so tabular, text, or vision, and the augmentation .py file. And so if we do flip left, right, and take a look at what we have here, we can see that we have a few different options based on these patches. And so if we have a PIL image that comes in, we'll run a specific version. If we have a tensor image that comes in, we'll run this. And so now we can have the same transform apply to various objects. So that's a little bit more into the nitty gritty of how everything is working. I hope that can kind of help you with any custom implementations you're trying to do. Again, we'll explore that more in a few weeks whenever we deal with the Gaussian heat maps and the pose detection. But that's about it for today. Feel free to let me know on the forums if you have any questions, or if any bits of the notebook might not work. The API is always changing, and I try and stay on top of it as best I can. But sometimes I might not get to it right away. I am still in college. But thank you guys for joining me today. It was a pleasure having all of you. Feel free to ping me if you guys have any questions. Thank you.